Hey everyone, welcome back to Chemistry 1111. Dr. Carroll here. We're looking at Unit 8. This is the second lecture about intermolecular forces. Remember way back in Chapter 2 when we looked at gases and properties of gases? Well, today we're going to look at liquids properties and some solid properties as well. And the liquid properties we'll look at are surface tension. I'm using the PowerPoint and the mini text here. Surface tension, capillary action, viscosity, and vapor pressure. All are functions of intermolecular forces. So let's start with surface tension, which is sometimes given the lowercase Greek letter sigma. And surface tension is like a skin on the liquid. Technical definition is it's the resistance of a liquid to an increase in its surface area. So if you have a larger surface tension, it is harder to increase the surface area, to stretch the skin, if you will. The units are joules, because you're doing work to try to increase the surface area, and units of surface area are square meters. So joules per square meter is the unit. Surface molecules of a liquid have a net inward force of attraction forming a skin, and the toughness of the skin is called surface tension. If you look in the bulk of a liquid, let's say here's water, and the bulk of the liquid, there's no net pull in any direction. But the water molecules at the surface, well, there's no water molecule above, no liquid water molecule above the surface, so there is a bend down, and this eventually leads to beading in when you wash your car or wax your car, then the rain comes and it forms beads as your the water is trying to form spheres, and it's all related to the surface tension. Or to decrease the surface tension, to get dirt off the plate in the dishwasher, you use surfactants. It's essentially detergent, right? Dishwashing detergent, and that will decrease the surface tension, allowing the particles on the plate to be washed away. Here I am, an expert on washing dishes. I don't know if everyone would agree on that. I'll talk about capillary action in a second. Let's just see if there's a bit more about surface tension. I think there is. So let's see liquids. Condense a gas to get a liquids. This is page 373. Substances with higher intermolecular forces will have higher surface tensions, viscosities, capillary. We'll get to capillary action. So let's see. Liquid molecules, they don't escape easily in the bulk, but, well, actually, sorry, I didn't say that. They move free around in the liquid phase, and they are fluids because they can flow easily from place to place. So when you talk about a fluid, you're talking about anything that flows, whether it is a liquid or a gas. Something that flows is a fluid. Gases are less dense than liquids. Liquids don't expand or contract significantly with changes in temperature or pressure. So let's look at some properties. That was just a bit of an intro. The relative freedom of motion of liquids leads to three liquid properties: surface tension, capillary action, and viscosity. So surface tension here is, where's my marker? There it is. Greek letter sigma. Viscosity, Greek letter eta. There's really no symbol for capillary action. And look at this important key state concept. That's why it's called a key concept, right? Substances with higher intermolecular forces have higher surface tension, higher viscosities, and lower vapor pressure. Water has a high surface tension because it's got lots of hydrogen bonding, which means it has high intermolecular forces. And we'll look at the other properties in a minute. If you have a small amount of liquid, the liquid tries to get in a sphere to minimize the surface area. Water drops from a faucet are nearly spherical. Mercury drops are nearly spherical. Surface tension measures the resistance of a liquid to an increase in surface area, is a physical property responsible for that behavior. Okay. One thing I should say, I don't think the book does, as the temperature goes up, typically the surface tension goes down. And so here we have a cool thing. A water strider is supported on water because of surface tension. I remember as a kid having this little sticker book of insects, and like you'd lick the insects and put the stamp down. And my favorite one was these water striders or walking sticks because it was so cool. They can walk on water, and you see why. There's surface tension of the water is not destroyed by the water strider on there because of the pressure exerted by the water strider isn't so great, because look at those feet, right? They have a large area. Remember, pressure is force per unit area. So if you have a large area, the pressure isn't as much. And so I thought that was always cool. Polar molecules such as water have high surface tension. Non-polar molecules like hexane have low surface tension because they have smaller intermolecular forces. Okay. A liquid is most stable when the fewest molecules are at its surface. What else can we say about surface tension? Water droplets tend to beat up and roll off a freshly waxed car. Related to surface tension is the idea about cohesive and adhesive forces. Molecules in contact with the surface of their container experience two sets. So if I have, well, here's water in a beaker, right? And I have adhesive forces of attraction between the water and the glass wall, and then in the middle I have water with water, which is cohesive. So we have two kinds of intermolecular forces. Cohesive attract molecules in the liquid to one another. Adhesive attract molecules in the liquid to the walls. So one result of this is the curved surface of a liquid called the meniscus, right? Here water has a concave meniscus. Okay, so the adhesive forces are greater than or smaller. Let's see. Adhesive forces are stronger than the cohesive forces. Right, so it creeps up a bit, so you end up with a concave meniscus. However, mercury, you may recall when you're looking at a thermometer, mercury, the cohesive, are greater than the adhesive. So your meniscus is convex for mercury. So it's concave for water, convex for mercury, and that's where you make your readings, of course, on a level surface, right? Okay. Now, there's another interesting phenomenon called capillary action, where water can climb the walls because you have stronger adhesive than cohesive forces. You can put a glass straw into water and you'll see it creep up. So it's actually going against the force of gravity action. And I'm not a biochemist, but I think of the word capillaries and veins, and it's got to be related. There's also, I'm not a botanist, but I see capillary action between sap and the cellulose walls of wood fiber plays a role in how trees transport sap from their roots to their highest branches. Okay, so that's a bit of information on capillary action. Let's see if our slides have anything to add to that, because before we get to the next one. So surface tension, we looked at that. Capillary action, the upward movement of water inside a capillary. So capillaries going to have small cross-sectional area against the force of gravity. Due to large forces between the glass and the water, then among water molecules, in other words, adhesions greater than cohesion, we'll get capillary action. And then we get to viscosity, which also is greater at stronger intermolecular forces. And this is really the thickness, the rate of flow of something. You can think of ketchup as being viscous, or molasses, whereas water or ethanol is not very viscous. Depends on the intermolecular forces, depends on the length of the carbon chain. Okay, you're going to be more viscous if you've got longer carbon chain. Depends on the temperature. Higher temperature means less viscosity. And you sometimes see commercials for engine oils and they talk about viscosity breakdown because there's high temperatures developing in your car engine. So you have to have an oil that isn't going to break down and have metal gnashing against other metal. That's not a good thing. So you need a good viscosity, and of course you can talk about 10W30 and 5W30 and these different engine oils and their viscosities. Okay, do we have another slide here? Let's see, what's the next one? Oh, we'll get to vapor pressure in a second. So let's go back to viscosity. Water can be poured very quickly from one container to another. Salad oil more slowly, and honey takes forever. Well, forever is a long time. Viscosity measures how easily molecules slide by one another. This depends strongly on molecular shapes. Water, acetone, and benzene, small, compact, have low viscosity. Large molecules such as sugars and honey, hydrocarbons, and oils get all tangled with each other, so it takes longer for, well, actually the experimental way to do this is you have a column with the viscous liquid in it, and you actually take a ball bearing and you drop it, and you see how long it takes to go to the bottom. Now, that's really low tech, but that's it's called a viscosometer or viscometer. I forget the name of it, but that is the instrument that can be used to measure the viscosity. And of course, it's relative. You compare that to another one. So if you have strong intermolecular cohesive forces, that also makes it harder for molecules to move about. We also said at higher temperature, the viscosity decreases. If you have hot honey or hot syrup, it's going to be much more easy to pour when hot than when cold. And here's, this table we should have talked about before. Some surface tension values. You see the surface tension increases. Here's water. Hydrogen bonding is more than the others. Some of them are hydrogen bonding, some of them just dispersion. But there's metallic bonds, which we'll get to either this lecture or the next, where the surface tension is much higher. Okay, so that just snuck in there. Viscosity can also be decreased by dilution with less viscous solvents. And in the tar sands in northern Alberta, you can put in liquid hydrocarbon solvents to try to dilute the heavy oil, reducing their viscosity, allowing them to be pumped up more easily. So the viscosity and the chemical engineering world are important and related to each other. Okay? So, when we also talk about liquids, we talk about vapor pressure. Some of the molecules will escape into the gas phase if a liquid has an exposed surface, like just a glass of water. There's a distribution of kinetic energies. Some of the molecules in any liquid will have enough kinetic energy to overcome the intermolecular forces and escape. And if you cover the lid, the pressure above the liquid at a given temperature is called the vapor pressure of the liquid. So you have a two-phase system, right? You've got the liquid and then you got the vapor above the liquid. It's all covered, and that's the vapor pressure. And the vapor pressure, sometimes called P-VAP, is related to the temperature. It's not a direct proportion. There's logarithms involved, but we just know that if the pressure of vapor pressure will increase, temperature increases as well. Okay, not linearly, but they both do go up. The equation, I don't think we talk about in this course. We'll check later, and I'll tell you about it. It's called the Clausius-Clapeyron equation if we do, but we'll talk about that later if necessary. Right now, just qualitatively, the hotter something is, the greater vapor pressure is exerted by it. And if you have two chemicals at a given temperature, the one with the stronger intermolecular force will have the lower vapor pressure. The one with the weaker intermolecular force will have a greater vapor pressure. We say the weaker molecular forces ones are volatile. Okay, they have a greater vapor pressure at a given temperature. Okay, let's see what else we got here. Smell of gasoline around an open tank informs their nose that the gasoline molecules escape from the liquid into the gas phase. Evaporation of a rain puddle talks about that as well. But again, you have to be in an equilibrium system to actually measure the vapor pressure. So let's see here. There's a picture A16 which is comparing bromine and water, and you see that the escape energy for bromine is less than water, so the intermolecular forces in bromine are less than water. Again, the hydrogen bonding is more important. And you also see that if you increase the temperature, you're going to have a greater vapor pressure. Okay. So the fraction of molecules with enough kinetic energy to escape a liquid depends on the strength of the intermolecular forces and the temperature. At 300 Kelvin, more bromine can escape than water. And at 320, for each one, you get more escaping. Here is just a preview in figure 817 about equilibrium. So here we'd have a vapor pressure of 0. The liquid molecules are not yet escaping. Now they are. And then when we get a rate at which the escape from the liquid is the same as the condensation back into the liquid, then we have a vapor pressure. And that's called the dynamic equilibrium. So when the rate of vaporization equals the rate of condensation, rate of vaporization equals rate of condensation. When that's true, an equilibrium has been created, but doesn't mean things stop. It's not a static equilibrium like in physics. It's a dynamic equilibrium, so molecules keep moving. And at a greater temperature, the vapor pressure is greater. We already talked about that. Okay. What are these here? Section exercises. Shall we look at this? The alcohol N-pentanol is more than 10 times as viscous as hexane. Well, it's got a, let's see, they both have zigzag kind of backbones. Yes, there's one more carbon in hexane, so you're going to say, well, why would N-pentanol, N stands for normal, why would normal pentanol be so much more viscous? And the key is you get hydrogen bonding in N-pentanol. You don't get hydrogen bonding in the nonpolar hexane, normal hexane, so that's why it's more viscous. Mercury is convex. We talked about cohesive greater than adhesive. You can draw that, and you can try to practice problems on your own. So let's push ahead a bit and jump to 8.4. Let's just see if the slides had any words of wisdom. No, they didn't. Okay, so we're going to look at forces in solids. And forces in solids may include dispersion forces, dipolar, hydrogen bonding. So all the ones we looked at before, or those ones we looked at before, but we can also talk about metallic, covalent, and ionic bonding. And we've looked a bit about covalent and ionic bonding earlier in the course. Okay, so you have rigidity in solids, locked in position. Things still vibrate, but certainly you don't get this free-flowing movement like you do with liquids, or the more extreme free-flowing movement when you're into gases. And there's lots of applications. So we have an immense range of melting points for solids, and there's a wide range of forces depending on the solid. Okay, so you can have covalent bonding, metallic bonding, which is delocalized electrons. The electrons are like a sea with the protons being like the anchors. So it's called an electron sea. Sometimes it's called an electron gas even, and ionic interactions. And there's 4 types of solids: molecular, metallic, network, and ionic. So this little section, there's lots of taxonomy involved. If you remember the word taxonomy, it's classifications. Taxonomy, if I can spell it right. Taxonomy. Okay. So table 8.4 contrasts the forces and energies in these solids. Table 8.4, where is that? Because that's a very important table. It's on page 377. Let's jump there. And then we'll look at each one. So we have attractive forces to keep solids together. One is called a molecular solid, and it could be just dispersion. So for example, argon, if you cool it to less than 84 Kelvin, it's a solid, and it's only dispersion forces which keep it, and to break it up you would need between 0.05 and 40 kilojoules per mole, typically for a molecular solid. So molecular solids do not have high melting points. I don't want to say boiling points, but that's true, but we're talking about solids to liquids, so it's melting points. Then I can have a molecular solid again, but it can have some polarity to it, so it can have dispersion and dipolar forces. For example, HCl, so you've got hydrogen chloride and then another hydrogen chloride, and look at the melting point, it's much higher. So if you have a molecular solid, well, it's going to have dispersion in it, but if it's also a permanent dipole interacting with another permanent dipole, you will have a stronger intermolecular forces attraction, more energy involved. You can also have a molecular solid where you got dispersion and dipolar, but the dipolar is hydrogen bonding variety, right? So water, right? Ice. So you're going to have your hydrogen bonding. Here's your hydrogen that's involved in the hydrogen bond. You got an oxygen here, and then it's attacking the lone pair on this other oxygen, and that's hydrogen bonding. I remember doing a project on hydrogen bonding. This was 1986. We did a broadcast feature on the computer where I sent a message to a group in Sweden, Uppsala, Sweden, and I was working at McMaster, and it was so exciting to actually send a message over a computer. This was before email. This was before the World Wide Web. This was when just things were starting. And I think sometimes I should have capitalized on that idea, that excitement of internet in its infancy, 1986, all right? But I didn't, and that's the way it goes. So the melting point, water, 273 Kelvin or 0 degrees Celsius. So you see hydrogen bonding there. So, but it's still, water is a molecular solid. You got molecules held together to other molecules through intermolecular forces. Now, if I look at a chunk of metal like copper, Cu, then we have this, what we call the electron sea. The electrons are delocalized through the whole system, and that is really strong, as you see here, bonding. And something like copper, if you want to melt copper, you got to crank in lots of energy. Temperature reflective of that, 1357 Kelvin. You can have a network solid, which is just a bunch of covalent bonds repeating each other, like quartz, silicon dioxide, and those can be quite high boiling points or melting points as well. Look at this one, SiO2 1983. And then you can have ionic bonding, which we looked at a bit before, with ranges, things like sodium chloride, 1074 Kelvin is the melting point. So those are some descriptions of types of bonding, types of solids, what kind of bonding there are, and some examples. So very important table. Again, I might print that out on an index card and use that to help you. So let's take a look here. Molecular solid, dispersion forces, dipolar and hydrogen bonds. Metallic solid, delocalized bonding. Network solid contains an array, that means a repeated arrangement of covalent bonds linking every atom to its neighbor. Should I say repeated arrangement? Let's just say an array, fine. And an ionic solid contains cations and anions attracted to one another by electrical forces. So molecular solids, well, I basically talked about it. I don't think I need to add much more than that. Well, I can add a bit. Substances that are gases under normal conditions form molecular solids when they condense at low temperatures, like argon. Many larger molecules have sufficient dispersion forces to exist as solid at room temperature. Naphthalene, C10H8 on the side here, is a solid that melts at 80 degrees Celsius. So you don't need much to melt naphthalene. There's strong dispersion forces, and there's highly polarizable electrons, and that allows it to be in a crystal form at room temperature. Benzoic acid, it has a dispersion forces, has all molecular solids do, but it also has hydrogen bonding because of the carboxylic acid group, right? Carboxylic acid group. OH. And so this, you can get hydrogen bonding associated with that. Glucose, C6H12O6, here's a picture of it. It's got lots of hydrogen bonding because there's lots of OH groups, right? So that causes it to have a higher melting point than you might think if you didn't know what hydrogen bonding was all about. And so it's a solid at room temperature. And okay, what else about molecular solid? The molecules of a molecular solid retain their individual properties. Solid iodine is dark in color because individual iodine molecules absorb visible light. Iodine vapor is also colored. Glucose dissolved in coffee tastes just as sweet as solid glucose because the sweet taste of glucose comes from its shape, which is the same in the solid phase as in the solution. Okay, interesting. That was benzoic acid. Talk about the hydrogen bonding. Okay, then we go to network solids, which are interesting in their own right. And they have very high melting points in contrast to molecular solid. So phosphorus is a molecular solid, P4, whereas silicon is a network solid. So you have this repeated system. You see a whole bunch of silicon in there. Covalent bonds among silicon atoms connect all the atoms. Some people call a network solid a giant molecule. White phosphorus, which is a molecular solid, melts at 317 Kelvin, but silicon melts at 1683 Kelvin. I mean, really, you have a bunch of covalent bonds in silicon, so the bonding forces are much stronger than intermolecular forces. For solid silicon to melt, you need to break lots of those covalent bonds. Bond energy around 225 kilojoules per mole, whereas attractive energies due to intermolecular forces are less than 40. Diamond and graphite, the two forms occur naturally on Earth, are both network solids, but they have very different physical and chemical properties. Diamond has three-dimensional bonding, 1, 2, and it's a network solid. I mean, graphite is too, but graphite has these sheets, and the carbon's sp2 hybridized. Diamond, the carbon's sp3 hybridized. So these sheets of carbon and graphite slide over each other, meaning graphite can conduct electricity better, and its boiling point I do not think is as high as diamond. You check, let me know. Yeah, so these layers there. But they're both network solids. Titania, TiO2, alumina, Al2O3. These have extremely high melting points. And molybdenum sulfide and also is a network solid. Okay, then a bit of history. Carborundum is a mix of silicon and carbon, 1-to-1, and that's another example of a network solid. And it's used in cutting tools. Strong and wear resistant, but it's not as expensive as diamond. So here's an example. You have P4O6, which is a molecular solid, and SiO2 is a network. So P4O6 is molecular solid with dispersion forces, and SiO2 is the network solid. Okay, they are not metallic, they aren't ionic, so they have to be network or molecular. SiO2, it's a network solid, strong covalent bonds, we said all that. Each oxygen atom bonded to 2 silicon, each silicon bonded to 4 oxygen. Let's read that again. Each oxygen atom is bonded to 2 silicon, right? And each silicon is bonded to 4 oxygen. Three-dimensional array of strong covalent bonds. P4O6, the melting point is just 25 degrees Celsius. It's a discrete molecule, okay, so it's not this repeating network. Sure, you have strong covalent bonds within the molecule, but each molecule is attracted to others by dispersion forces only. Okay, so I would say there may be a little bit of dipole-dipole interaction, but the symmetry may make that very small. In any case, it's not much, so it's easier for the P4O6 to melt. Practice exercise 8.4. One neighbor of arsenic germanium melts at 1210, its other melts at 490. What type of solid is each of these elements? Well, germanium melts at 1210 and selenium just at 490. So they are not going to be the same kind, are they? Selenium is a molecular solid compared to germanium, which is a network solid. Now that's sort of a tough call to make, really. 1210, that's high, so I would agree germanium is a network solid, but selenium being a molecular solid, it's still at 490. I think that's sort of a nasty question to ask. I wouldn't ask that, or if it appears, I would give more detail about it. Okay, but relatively speaking, it'll be more of a molecular solid. Selenium will be more of a molecular solid than germanium will, because germanium's melting at 1210 degrees Celsius. Okay, metallic solids. We have again the C of mobile valence electrons, and that is the force for metallic solid. That helps give you that and allows the electrical conductivity to happen. Still, the strength is variable. Alkali metals are quite soft and melt near room temperature. We used to have alkali metals at the school, but safety people said we couldn't have it anymore. Sodium melts at 98, cesium at 28.5. So weak bonding for alkali metals. You only have one valence electron in what's called an energy band. But metals in the transition area, the D block, they're tough with high melting points because you've got lots of electrons, s electrons, d electrons to form these energy bands, and that gives you strong metallic bonding. Another thing to remember, maybe from junior high, metals are ductile, which means you can draw them out into long rods, and malleable, which means they can bend easily. Okay, changing the position of the atoms doesn't correspond changes in the energy levels. So the bonding nature doesn't change if you change the shape. Fine. Then you have range of properties for the metals. Okay, metallic bonding. Ionic solids we've already looked at before. There you have separate cations and anions attracted to each other using electrical forces. So the forces act between the ions rather than between the molecules. And okay, that's fine. So we have, you can also have a metal cation and polyatomic anion. Lots of ionic solids have that, such as sodium hydroxide, potassium nitrate. Here we have your copper sulfate, or copper Roman numeral 2 sulfate, barium carbonate, sodium chloride, and some others. And you can even have more than one cation or anion in some of these mixes here. Okay, a little bit on superconductors. You can look at that on your own, and we can look here, section exercise 8.4.1. So let's look at that for a second here. What's carbon dioxide? It is a molecular solid with dispersion forces between the molecules. Dry ice, solid carbon dioxide. Crystalline yellow elemental sulfur, that's going to be a molecular solid with dispersion forces between the molecules. Tin, that is going to be a metallic bonding, holding the atoms together. Not one of the strongest of the metals, but there. Lithium oxide, we know, is a ionic system with electrical attractions between La plus and the O2 minus. 8.42, let's try that one too. Arrange the following orders of increasing melting point. Carbon and diamond, F2, K, or CO. Well, I'm going to go with F2 first because I think that's a molecular solid, so it's going to be weakest. And I think diamond, being a metric solid, is going to be the strongest. So then I got potassium and cobalt. I'm going to put potassium and then cobalt because alkali metals are sort of soft and have lower melting points. Are we right there? Let's see. The order of melting is F2KCOC. F2, yeah, hooray! F2 is molecular with dispersion forces only. K and CO are metals, but cobalt has more valence electrons resulting in stronger bonding. Right. Diamond is a network solid with stronger covalent bonds. And then you can try the next part there. And you can read about superconductors. Maybe some of you one day will work in a company that's making superconductors and can help save the world. Okay, order in solids, I think we're going to make that the next lecture. So that'll become lecture 3 in unit 8. Let me see if there's some more stuff that the slides have that we didn't look at. Intermolecular forces. There's that beautiful table. Molecular solids. Yeah, network solids. Diamond versus graphite. That's always, I always see that on a test or exam. Tell us similarities and differences between diamond and graphite. They're known as allotropes, allotropes, allotropes of carbon. Okay, we did that one. Metallic solids. Good. Ionic solids and superconductors. Okay, you can read about that. Then we get to order in solids. Sounds good? Have fun.